Hello friends, in previous lecture we have studied every sequentially compact matrix space is compact. Lastly, we have proved every totally bounded matrix space is separable. Compact matrix space is separable. Now we have to learn equivalence between compactness and sequential compactness. For that, first we will talk about Lebesgue number and Lebesgue covering lemma. So what is the Lebesgue number? Let XD be a matrix space, XD be a matrix space, and if you take C be covering of X and C is equal to say G alpha, alpha belongs to index set, be open covering of X, be open covering of X, then number delta greater than 0, then real number delta greater than 0 delta greater than 0 is said to be Lebesgue number, Lebesgue number for C. For that covering C, if for C, if every set A in X, if every set A in X with diameter of A less than delta is contained in some G alpha, belongs to C, that covering. So this is the definition of Lebesgue number. Okay. Now Lebesgue covering lemma. Lebesgue covering lemma in sequential compact matrix space, in sequentially compact matrix space, we know that sequential compact matrix space is always compact. Every open cover has a Lebesgue number. Every open cover has a Lebesgue number. If XD is sequential compact matrix space and C is, that is, if XD is sequential compact matrix space is sequential compact matrix space and C is open cover of X, then X has then C has Lebesgue number. C has some Lebesgue number. Okay, this is your Lebesgue covering lemma. We'll assume this Lebesgue covering lemma without proof, and our aim is to prove that every sequential compact matrix space is compact. is compact. Okay. Theorem. Every sequentially compact metric space is compact. So let XD be sequentially compact metric space, sequentially compact. One. What is our aim? XD is compact. XD is compact. That is, every open covering of X has finite subcover. So let C be some open covering of X. Has a positive Lebesgue number, has some positive Lebesgue number. Okay. So let C be open covering of X. Now since X is sequentially compact, therefore by Lebesgue covering lemma, now since X is sequentially compact, therefore by Lebesgue covering lemma, C has Lebesgue number say delta greater than 0. Say delta greater than 0. Again, X is sequentially compact and hence totally bounded. Therefore, for each epsilon greater than 0, X has finite epsilon net. Therefore, for each epsilon greater than 0, X has finite epsilon net. Okay. Whatever your choice epsilon may be, in particular, X has delta by 3 net. X has delta by 3 net, finite net. X has finite delta by 3 net, say A is equal to x1, x2 up to xn. Then your X is contained in X is equal to union of S delta by 3 xi, I equal to 1 to n, I equal to 1 to n. Now since diameter of S delta by 3 is at most 2 delta by 3. The radius is delta by 3, so diameter become at most 2 delta by 3, it may be less than that. Okay. Now diameter of S delta by 3 xi is less equal to delta by 3, less than delta, and delta is Lebesgue number of C implies d S delta by 3 xi is contained in J alpha I for some J alpha I belongs to C, I equal to 1 to up to n. Therefore x is equal to union of S delta by 3 xi I equal to 1 to n must be equal to union of G alpha I equal to 1 to n. Implies G alpha 1, G alpha 2 and so on, G alpha n is finite subcover of x from C. Okay. Thus every open cover of x has finite subcover. And therefore XD is compact metric space. XD is compact metric space. Thus every sequentially compact metric space is compact. Corollary: closed subset of complete metric space is compact if and only if it is totally bounded. Corollary: closed subspace of compact metric space of complete metric space is compact if and only if it is totally bounded. So suppose A be closed subset of complete metric space XD. Suppose A is closed subspace of closed and totally bounded subspace of complete metric space XD. Now, since closed subspace of complete metric space is complete, closed subspace of complete metric space is complete, implies A is complete and totally bounded. Complete and totally bounded subset of complete and totally bounded subspace is sequentially compact. Totally bounded subspace is sequentially compact and hence compact. Okay. Conversely, suppose A is closed subspace of A is compact subspace of A is compact subspace of complete metric space XD. Metric space XD. Since compact subspace is sequentially compact subspace is sequentially compact, therefore A is sequentially compact and hence totally bounded Okay, thus the result is proved. The result is proved. Example, R is not compact metric space. RU is complete but not totally bounded, therefore R is not sequentially compact and hence not compact. Next example, Q intersection 01 is not compact subspace of complete metric space RU, as it is not closed, If it is closed, then it must be compact. It must be compact. Is it clear? It is totally bounded, but it is not closed. It is not closed. Okay. Then, if I take example 2 5 by 2, two 5 by 2 union 3 3 square by 3 square plus 1, that is 10 by 3 union 4 25 by 4 union so on n square plus 1 upon n, like this. Oh sorry, 4 square, that is 17. 17 by 4. Is not compact subspace of Ru, as it contains sequence 2 3 4 and so on, having no, which has no convergent subsequence, is not sequentially compact, as it has sequence which has no convergent subsequence and hence not compact, right? Next example, prove that C01 D infinity is not compact. Show that set of all continuous function with respect to supremum metric is not compact. Solution. Consider fnx is equal to, fnx is equal to n for every x belongs to 0 1. Then for every n belongs to n, then each fn is constant function and hence continuous. Implies fn belongs to C01 for every n. Now, distance between fn and fm, distance between fn, now for m not equal to n, in n, distance between fn fm is equal to supremum of mod of fnx minus fmx, x belongs to 0 1 is equal to mod of n minus m is greater equal 1 implies n equal to 1 to infinity has no convergent subsequence, because distance, any two functions at a distance greater or equal 1 subsequence, and therefore C01 is not sequentially compact, and hence not compact, So, in this lecture, we have studied every sequentially compact matrix space is compact via Lebesgue number and Lebesgue covering lemma, and then we have taken few examples which are not compact. So, till now we have proved equivalent conditions for compact matrix spaces. A matrix space XD is compact if and only if it is sequentially compact, if and only if it is totally bounded, and complete if and only if it has Bolzano-Weierstrass property. Okay, we will prove one more result about the compact matrix space. Compact matrix space is compact if and only if it has finite intersection property. Okay, so we will study that property in next lecture. We will stop here. Thanks for listening lecture carefully. If you like the lecture, subscribe channel and also give some comment about the lecture. Thanks.